Thank you, Alina, and good morning, everyone. Thank you for tuning in to the lecture from RCC. We're going to start the series with considerations of old versus new technologies. My name is Frank Ascoli. I work in Providence, Rhode Island. I am a medical physicist, and I've been there over 30 years. I've seen a lot of changes in technology, and in fact, at my own clinic, we have advanced from a Cobalt 60 unit all the way to a modern image guided linear accelerator delivering conformal radiation therapy with multi-leaf collimators. So I've experienced the whole spectrum, starting from Cobalt up to modern accelerators. And we're going to look at some of the key differences between old and new technology. And I use the word old with caution because it really is a relative term, and lots of people still use Cobalt, and Cobalt is still a very good modality for treating cancer if it's all that the clinic has. But this is a lecture which will show the progression from the Cobalt unit up to modern accelerators. We're going to start and focus mainly on beam energy and percent depth dose. What does energy have to do with dose at depth in a patient? We'll look at a Cobalt machine, and then we'll look at a linear accelerator and look at and explain the differences between the two. We'll also see the advances in technology from treatment planning, from 2D to 3D to conformal. Treatment planning is not the focus of this lecture. That will be coming up in further lectures and future lectures. I'll show some examples from my clinic, and we'll look at image-guided radiotherapy with a linear accelerator. But the focus today really is on energy and dose and Cobalt to linear accelerators. So some history here. Of course, Röntgen discovered X-rays in 1895, and the first treatments began soon after that. It was noticed that cancers of the skin would begin to recede on these early pioneers of radiation, that cancers would begin to recede when exposed to these X-rays. And radiation therapy actually began a year after the discovery of X-ray. William Coolidge introduced the Coolidge tube in 1913, but then he also increased the voltage to 200 kilovolts, and it was called deep therapy. From 1940 on, we saw orthovoltage energies from 50 to 250 kV, and then of course radium with the Curies, and radium was used as a source of brachytherapy. And finally, to begin the end of the X-ray tube orthovoltage range and the beginning of Cobalt, we have, in the interim, we have Van de Graaff generators, which were used in and around Boston. I actually had the opportunity to work on a Van de Graaff generator early on in my training. And these were used for the production of high energy X-ray. So much of old versus new technology really focuses on the ability to deliver energy to the target. So the linear accelerator has progressed, but it has progressed mainly in the direction of focusing the beam, improving the accuracy of dose delivery, while the fundamental technology doesn't change too much. So what we want to look at first, as we look at Cobalt versus Linax, is the effect of depth on dose. As a beam of radiation, photons, enters tissue, it releases secondary electrons through the ionization of the atoms of the tissue. Those secondary electrons, depending upon the initial energy of the radiation beam, travel either minuscule, either a very small distance or a very deep distance, depending upon the energy of the incident radiation. And where those electrons deposit their dose, their ionization, is the phenomena, is the thing that we call depth dose. Now, because the electrons are released immediately at the surface of the skin, there is actually not a lot of dose delivered at the surface of the skin with high energy radiation. The electrons travel further and further before they deliver their dose, and that gives us the buildup region. So the buildup region goes from a very low dose up to a very high dose where that initial wave of electrons delivers their dose, and that is the buildup region. It's also called the skin sparing region, and this is the big difference between orthovoltage, low energy, low kV radiation, and megavoltage, which is cobalt and beyond. The phenomena of skin sparing, the idea of not delivering 100% to the surface, but delivering that 100% a little bit beyond the surface, is one of the greatest features of modern day radiation therapy. As energy increases, there is more skin sparing because the electrons have to travel further to deposit their first wave of dose. This is shown by curves called depth dose curves. And in this slide, you see depth dose curves starting with very low energy, 120 kV, and it goes up to 100%. At the surface, there is no skin sparing. And then the next curve, 250 kV, it doesn't show the yellow line here, but imagine that going all the way to 100% again. There is no skin sparing at energies from 250 and less. The very first time we saw skin sparing was right here with Cobalt 60. And see this little peak right here? See the difference? The peak is not at zero. The peak is down here at around 50, 60, 65, 70%. The surface is here. The peak occurs at a depth of 5 millimeters. Half a centimeter is where you get 100%. And that first half a centimeter is called the buildup region, and that is the region of skin sparing. If you take the graph and turn it into numbers, you'll see that superficial orthovoltage have no skin sparing, 100% at the surface, but it's not until you hit Cobalt 60 energy, which is 1.25 MeV, the beginning of megavoltage. It's not until you hit Cobalt 60 that you start to see a half a centimeter of skin sparing. And then as accelerators took over and the energy of the linear accelerators began to increase, you can see how deep the dose maximum becomes, even as high as 5 centimeters with 25 MV. And in fact, early on in my career, I worked with Siemens Betatrons, which had an energy of 45 MV. We were working with 45 MV beams, and the Dmax was beyond 5 centimeters. It was close to 6 centimeters before you built up to maximum dose. Today, in modern radiation therapy, we use mainly 6 MV and 10 MV. And you can see the skin sparing is about 1.5 to 2.5 centimeters. So orthovoltage at 0, cobalt at 0.5, and as energy increases, the depth dose increases and the skin sparing increases. This is shown in a diagram here, which shows two fields, one coming from the patient's right and one coming from the patient's left. Now, if you had a dosimeter and you could measure dose from the midline all the way out to the surface of the skin. So this patient is 25 centimeters in diameter, and a beam comes in from one side and a beam comes in from the other side. Let's say you wanted to give your dose at the midpoint here. Look at what happens as a result of beam energy. Now with cobalt, I'll go back to the cobalt curve here. With cobalt, you can see that there's this 100% and then a depth dose. And at 25 centimeters, you can see the depth dose is actually very low. At the midpoint here, 12.5, the depth dose is about 50%. What this means is literally to give the dose here at midline, you would have to give double the dose here at the surface because of the depth dose, but you do get some skin sparing. See, it doesn't go all the way to zero. See, there's that peak there, there's that peak there. As a function of energy, look at though, because the depth dose is increasing, how less the given dose, the dose at D max, begins to decrease as you go up in energy. And in this range here, look at 10 MV. How nice this is here. It's almost flat across. See that? Look at that. You give the dose here, and you only get about maybe 8% more. But with cobalt, you're giving 120%, maybe 122, 123% to the surface. So this is the phenomena of dose at the midpoint affecting the given dose at Dmax. And you can see how much this is improved by increasing the energy. You don't have to give as much to the surface to get the dose at depth. You don't have to give as much at the surface to get that dose at depth. I'll turn the lecture over to Alina for a Zoom poll. The Zoom poll here is using this figure, approximately how much dose does the skin receive if the midline is treated to 70 gray? So you're giving 70 gray here, parallel opposed, cobalt 60. How much is the skin dose when that happens? And these are your four choices: 60 gray, 70 gray, 76 gray, or 84 gray.
And Frank will give everyone about 15 more seconds to.
Okay, well, I'm pleased to report that most people got it right at 84 gray. The idea that you're giving 70 gray here at the midpoint with cobalt 60, as you look at this graph here, the given dose is about 120%. So you have to give the equivalent of 84 gray to get the 70 gray in the middle. Don't forget the depth dose at 12.5. If you look at this curve here, the depth dose at 12.5 is only 50%. So to give 35, if you're giving 35 gray from each side divided by 0.5 equals 70 gray immediately at the surface just to get 35 at depth. So you're giving 70 gray from one side, 70 gray from the other side, but you also have to remember that there's also exit dose. The exit dose adds to that, and that's what builds it up. That's what builds it up to 120%. So it's not just 100%, it's actually 120% because there's exit dose. In 1940, patients were treated with low energy radiation for many different sites. And this is an example of radiation burns from low energy radiation. In order to get the dose at depth, even with buildup, even with the half a centimeter from cobalt, there was still some skin burning because the Dmax was only half a centimeter from the surface of the skin. Finally, in the 1950s, Harold Johns from Canada was able to encapsulate a cobalt source and put it into a treatment machine, focus the beam with lead collimators. The advantage of using cobalt over orthovoltage radiation was that you had higher dose rates at a further distance from the patient. It was important to get further away from the patient, 80 centimeters. The early cobalt machines were actually 50 centimeters, and then they progressed to 80 centimeters, and then finally 100 centimeters. But it's important to move the source away from the patient because that improves the depth dose of the beam. So higher dose rates at higher source to skin distances. Cobalt energy at 1.25 MeV gave some skin sparing compared to orthovoltage. And cobalt remained a very good source of treatment for many, many years and for millions and millions of patients. The skin dose was still high and there was still burning, but nothing like the burns that we saw with orthovoltage. And as a physics aside to that, to the higher energy of cobalt, there is also a phenomena of the absorbed dose to bone. With low energy radiation, the absorbed dose to bone was much higher than the dose to bone from cobalt. And this has to do with how energy is absorbed by tissue at different energies. So bone did not absorb more dose than the tissue around it with megavoltage radiation. But with X-rays, the bone dose became sometimes twice as high, sometimes 3 times as high with X-ray machines. So the doctors that delivered these X-ray therapies at low energies had to be very careful of bone dose if bone was in the field, because at low energy, bone can absorb 2 to 3 times as much as tissue. But at high energy, bone and tissue absorb about the same amount of dose. So there is less heterogeneity and more homogeneity in the dose surrounding bone. This is a modern cobalt machine, and you can see that the cobalt head can actually rotate around the patient, giving an isocentric treatment. And the cobalt is in the head of the machine here, and the adjusting collimators are here to focus, to shape the beam. Cobalt is a simple machine to operate. The source is right here, and it's on a sliding draw, and it's driven by air. So an air piston drives the source from its closed position, where it's shielded, into the position above the collimator here, where the beam can focus down toward the patient. So it goes from off to on here, and the beam is shaped by the collimators. One of the other phenomena that we see with linear accelerator shown in this film versus cobalt shown in this film is the edges of the field. So cobalt has a very fuzzy edge called penumbra. You can see it right here, how it goes from light to dark, and it takes a while. But here's a film of a linear accelerator field, and you hardly see a field edge here. The penumbra is much, much sharper, and it's shown in these isodose curves. This region here, the edge of the field, is called a penumbra, and it's tight with linear accelerators because the source for a linear accelerator is very tiny. It's only 2 or 3 millimeters is the target area bombarded in a linear accelerator. But in a Cobalt 60 machine, the source is over 2 centimeters in diameter, and it creates this fuzzy penumbra, which makes it hard to control the dose to the surrounding areas. So to give dose in the middle, there was actually significant dose given along the edge. Here is the Cobalt source here, 2.5 centimeters. And if you draw, using geometry, if you draw lines from the edges of the source, you'll see that this area here is a penumbra of the Cobalt beam. So even though you want to treat this area here, you give significant dose to the edges of the field. So penumbra with Cobalt 60 was pretty significant. This was 2.5, 25 millimeters across, but in a linear accelerator, the source of the radiation in a linear accelerator is only about 2 to 3 millimeters in diameter. You can see how many linear accelerators were sold beginning with in the 1980s. It took off. So many linear accelerators were being sold. There was still Cobalt in use, but it began to drop off as more and more linear accelerators came into use. So in 1970, when I started working in radiation therapy, we had the variant Linax 4, and it was a very modern linear accelerator at that time. And it produced an energy of 4 million volts equivalent. The reason the linear accelerator was popular and was able to be developed was because of microwave technology. So instead of a radioactive source, such as cobalt, instead of an X-ray tube like a Coolidge tube, the radiation could actually be produced by using microwave as the accelerator for the electrons. Let's look at the cross-section of a modern linear accelerator and just look at the major components of it. So different from a Cobalt 60 unit. Okay, so starting here at the rear of the machine, there is something called a gun, the electron gun. The electron gun injects electrons into the accelerating structure called the guide. Now, the guide could be very long, about 4 feet long. So it has to be mounted horizontally like this. The electrons are injected into the guide. Microwave is pumped into the guide, and it's the microwave energy that causes the electrons to accelerate at almost the speed of light before they come out of the end of the accelerator. So now these electrons are going at almost the speed of light, and they have to be bent toward the patient. The patient is lying here on the table, but the acceleration is occurring up here parallel to the patient. So there is this device called a bending magnet. A bending magnet takes the electrons and bends the electron beam 270 degrees to point it straight down toward the patient. So the electrons start at the gun, a filament, a hot cathode, bubbling off electrons. The electrons get swept into the guide, accelerated by microwave, come out at the speed of light, almost at the speed of light, bend 270 degrees around, and now are headed toward the patient. But before you can use that electron beam, it has to hit a tungsten target. So the electron beam hits the tungsten target, which is located right about here. And the tungsten target converts the energy of the electron into X-ray. Accelerate electrons, slam it into a piece of tungsten, out comes X-ray. The X-ray is then spread out by a flattening filter here. So it makes a nice beam that's shaped like a cone. Then there is a chamber, an ionization chamber in the head of the machine that monitors that radiation. So it can tell how many monitor units or how much dose is being delivered. And then the beam is shaped by collimators and by multi-leaf collimation to create some pretty exotic shapes. So modern accelerators, much higher energies compared to Cobalt, 6 MV versus 1.25, a bending magnet to bend the beam, tungsten to convert it to X-ray, flattening filter to make it nice and smooth across, and then collimation to shape the beam. Not just rectangles, not just squares and rectangles, but any shape you can imagine. To show this a little bit better, how a linear accelerator produces radiation, this is a nice cross-sectional diagram that shows the cathode here boiling off electrons. The electrons get swept into this guide. The microwave accelerates the electrons at almost the speed of light. The microwave can carry the electrons very, very fast through the guide. They come out at almost the speed of light. They enter this bending magnet. Because electrons are charged particles, they are affected by a strong magnetic field. That magnetic field can bend these electrons and focus them onto a piece of tungsten, which is called a target, and then radiation gets emitted from that target. A flattening filter here to shape the beam, and a ionization chamber to measure the beam, and then collimation to shape the beam. So we start with electrons from a gun, accelerate at almost the speed of light, bend them around back to the patient, produce the X-ray right here with the target, flatten the beam, make it smooth, and then shape the beam. So let's compare the technologies, Cobalt versus linear accelerator. Cobalt has a lower energy, 1.25 MeV, and a higher penumbra. Relatively low dose rate, higher dose to the skin. Even though there is skin sparing, it's still a higher dose to the skin than a linear accelerator. Higher dose to healthy tissue because of the penumbra. Treatment planning was 2D, so we didn't have the advantage of three-dimensional planning and treating a volume. It was all treated in a cross section. Everything was planned as a cross section on a flat piece of paper, and we didn't have the ability to take computerized images and make it into a volume. Only planar flat images were used. And these are some terms I'm going to introduce now. I'll explain them to you, but you'll hear much more about this in upcoming lectures. The GTV is the gross tumor volume. That's the actual tumor, the tumor volume, the gross tumor volume. The CTV stands for the clinical treatment volume, and it's the tumor and how far it has spread around the middle of the tumor. So the clinical tumor volume is the spread around a tumor. The planning treatment volume is very important for physics and dosimetry because the planning treatment volume is what the doctor wants to cover. The planning volume is always bigger than the GTV and the CTV because the doctor has to cover more area around the tumor because the doctor knows that the tumor is beyond spread what the doctor can see. And then there is the idea of an ITV, an image treatment volume, an image treatment volume. And the ITV, the image treatment volume, has to do with motion. If a tumor moves up and down with breathing, then the ITV has to be even bigger. Multi-leaf collimators, MLC, stands for multi-leaf collimator, usually not available, and shaping was done by a low-temperature alloy called cerumen. Cerumen blocks were used. In modern accelerators, 6 MeV and above compared to 1.25, so better skin sparing, less penumbra, better depth dose. Much higher dose rates, shorter treatment times, less patient motion. Shorter treatment time means less chance that the patient can move. There's less skin dose with accelerators. Better tumor coverage, more conformal. We have asymmetric jaws with a modern accelerator, which means that a single jaw can be moved. So a field can still be a square or a rectangle, but it can be shaped to one side of the center axis. It can be asymmetrical. MLCs, multi-leaf collimators. Enhanced dynamic wedge, EDW, enhanced dynamic wedge, where by moving a jaw of the linear accelerator through the radiation field, you can actually get the shape of a wedged beam without using a mechanical wedge. And two big advances with linear accelerators was onboard imaging, OBI, onboard imaging, where the linear accelerator now includes an X-ray tube to take a CAT scan, a CT scan of the patient. And then image-guided radiotherapy that you'll be hearing more about, where the image that's taken with the CAT scan is targeted, the patient is adjusted for any small daily differences in position, and then the beam is delivered. So with modern accelerators, there's an image taken first, and then the patient is adjusted based on that image and then treated, all in the same session. Many advances in treatment planning, such as CT simulation, so using a CAT scan instead of an X-ray machine to plan the patient. And because you're using CAT scan, you have corrections for the different tissues, such as bone, fat, muscle, glandular tissue. The CT scanner gives you the CT numbers for these different tissues that can be then put into the planning system, and any minor dose differences between soft tissue and bone can be taken account of in the planning system because you now know what those densities are from the CT scan. Then there's IMRT, intensity modulated radiotherapy, volumetric modulated arc therapy, VMAT, where the machine rotates around the patient, the linear accelerator rotates around the patient while the MLC is moving, giving you a very, very good control over the shape of the field. The PTVs, we spoke about the planning treatment volume. OARs are organs at risk, organs at risk. So now you can specify which organs you don't want to treat. And the computer can plan to deliver dose to the tumor and spare surrounding organs. With modern treatment planning, there was something called dose volume histogram analysis. So actually giving numbers for the tumor and giving numbers for the different organs around the tumor. So not just curves and lines, but actually giving a table of numbers that looked at dose, the volume receiving that dose, and the type of tissue. Is it the tumor or is it the organ at risk that you want to avoid? Inverse planning systems where you put in how much dose the tumor should get, you put limits on how much dose the surrounding tissue should get, and the computer takes over and develops the ideal plan for you. Inverse planning. And then another feature of a linear accelerator department, which has treatment planning and CAT scan, is the networking that takes place. So in a department, there is a computer network that connects the CT scanner to the treatment planner, to the treatment planning computer, back to the machine, so that everything is controlled by computers. And it also allows for treatments which are very, very high dose. And those treatments are called SABR, stereotactic ablative body radiation. Basically, stereotactic radiotherapy, it's called. Stereotactic ablative body radiotherapy, and stereotactic radiosurgery, where the dose is given all in one fraction. In these treatments here, instead of the patient being treated for a week or 2 weeks or 3 weeks, the patient is only treated in 4 or 5 fractions with very high dose. You can do that with a linear accelerator because the linear accelerator doses are so high. You can give a lot less fractions with higher dose, and that's called stereotactic treatments. And if you gave the treatment all in one dose, say to a tumor in the brain, gave it all in one dose, that's called radiosurgery. Motion management systems come about with linear accelerators because now you can have computers monitoring the patient motion and actually adjusting for motion during the treatment. Integrated motion management system. And of course, on the computer side, you have record and verify. So if the computer network connects the CT scanner to the treatment planning system, back to the linear accelerator, there is a record stored in the computer memory of the patient, the area being treated, what the field sizes were, how much dose was being delivered, how many monitor units, who delivered the dose, a record and verify system that monitors and records what the linear accelerator is doing. I took a picture of a multi-leaf collimator to show the complexity of it on a linear accelerator. So this is looking down into the head of the linear accelerator with the covers taken off. Here you can see the primary jaws, X and Y. So these are the big lead jaws that are used to shape the field in 2 dimensions, to make square and rectangular fields right in here. But look at these tungsten leaves right here. There's 60 of them on each side. There's 60 in this direction, and there's another 60 in this direction. And each leaf is controlled by a motor right here. So 60 leaves and 60 motors, 60 of these tungsten leaves and 60 motors. So the leaves can shape the field even while the beam is on, and any shape is possible. This is an example from my clinic of a patient being treated with the field that's shaped like the letter S. And you can see how the leaves can shape that field. And even during treatment, these leaves will move in and out of the field while the beam is on. That's called volumetric modulated arc therapy. Here is an example that shows really how we have progressed in our technology. So here's a tumor, and tumors can be very irregular. They're not always nice and round. So here's a very odd shaped tumor. Now, when we treated before with square and rectangular fields, we would have to treat all of this. This whole square, this whole rectangle around the tumor, we would have to treat if we wanted to cover it all and allow for penumbra with a Cobalt unit. If we wanted to allow for penumbra with a Cobalt unit, look at how much bigger we had to make that field. Okay, and in this example, there's a sensitive organ right here, like let's say the spinal cord, or let's say a salivary gland or a kidney. There's an organ here next to the tumor, but you can't avoid it because you have to make the field this big to cover everything. So that was 2D radiation therapy. Okay, Okay, then we used multi-leaf collimators, 3D conformal. So in 3D conformal, you took a CT scan, which was in 3 dimensions, and you could shape the multi-leaf collimator, allow for penumbra, and get a little bit tighter, and get a little bit tighter. See? But you're still giving significant dose to the sensitive organ. But then finally, with intensity modulated radiotherapy, where the veins, the leaves change while the beam is being delivered, you can now shape the field and make these shapes pretty conformal around the tumor, still allow for the penumbra of the beam and still allow for the clinical treatment volume, but you can shape the radiation much, much better with intensity modulated radiotherapy, IMRT. And it's this idea here that you could shape the beam from many different angles, which allowed for much, much better coverage of the tumor and less dose to the surrounding organs. Now, if you can shape the field and not do as much damage, you can give more dose to the tumor and you get better tumor control and less side effects. So as we moved away from cobalt, square, and rectangular fields, the linear accelerator produces radiation by accelerating electrons, slamming them into a piece of tungsten, but excuse me, but by using computer control of the linear accelerator leaves and by doing 3D conformal therapy treatment and intensity modulated radiotherapy treatment on your planning system, you get excellent tumor coverage while sparing normal surrounding healthy tissue. Better tumor control, less side effects. This is an example from a planning system, a treatment planning system, taken that was done with CAT scans of the head here, and you can see in white. You can see in white right here. This is a nice picture, and you're going to learn a lot more about this in future lectures. But you can see in white the area that the doctor wants to cover, and it's the same in all 3 images. Now, if you're using 2D treatment planning, square and rectangular fields, you have to come in from this side, you have to come in from this side. This is where the beams meet, and look at how much more you end up treating. You end up treating a lot of healthy tissue. If you use 3D planning, where the beam comes in and it's shaped a little bit better from 4 different directions here, 5 different directions, 1, 2, 3, 4, 5, 6 different directions here, shaping the field, you can get better tumor coverage and less dose to the surrounding tissue. But if you're using intensity modulated radiation therapy, the field can come in from many, many different angles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different angles, all shaped with the MLC, a lot less dose to normal tissue, and still get a high dose to the tumor. So this is the progress, and this is the dosimetry gain as we move from old technology to new technology. So I want to end by showing you some examples from my clinic in Providence, Rhode Island. This is what our department looks like. We have a CT scanner. It's made by Philips. It's a 16 slice. They call it a large bore scanner. It's much, much bigger than an ordinary CT scanner. It's made for radiation therapy, where you can put the patient on immobilization devices. This is a breastboard for treating breast cancer. The patient's head would be here, and her arm would be up here. So her arm actually hooks around, and it's held by these 2 things. And we can treat the breast without having her arm in the way. And all of this can fit inside the CT scanner. And so she is imaged in exactly the position she's going to be treated in. we have a lot of immobilization devices called vac locks. The vac lock helps to immobilize the patient's body in the position that we want to treat it in. So we make the vac lock. In here, you can actually see some of the bags hanging back here where we make the vac lock. We image the patient, and then we treat the patient using this immobilization. And this immobilization could be for any part of the body. It could be, you could immobilize the legs, the feet, you can immobilize the chest, you can immobilize the arms, you can immobilize any part of the body. Immobilize it, image it, and then plant it in that position. And these are unique for each patient. Each patient owns one of these. They have, so this is for all the different patients that we treat. This shows it on the table to immobilize the patient's feet. We're treating somebody's prostate, for example, and we want to keep his feet nice and straight. This is customized to his legs and his feet. We have a system here where we monitor the patient's body for movement, and it's called optical surface monitoring, OSM, optical surface monitoring. There is a camera mounted on the ceiling here. There's one above that you can't see, and there's another camera here. Now, the camera is looking at the patient's skin and looking for movement of that skin. Now, if the skin is moving, if the surface is moving because of breathing, the camera picks up the breathing motion and signals it back to the computer. And it looks like this. So here's the surface of a woman. We're treating her for breast cancer, and it's looking at her surface. It's looking at how the breast is moving during treatment. And it's looking at 6 different directions: vertical, longitudinal, latitudinal, and then yaw, roll, and pitch. So this is X, Y, Z, and these are the rotational. And it gives you the movement what's acceptable. So you set the acceptance limits. See over here, let's say you don't want it to go beyond these green lines for X, Y, Z, and for roll theta and phi, for roll, pitch, and yaw. And as long as it stays green, the patient isn't moving as much, and you could treat with not much difference on the dose. But we have a technique that we've developed. A lot of people are using this technique. It's called breath hold, where if you could get the patient to hold her breath, take a deep breath and hold it, these lines become very steady. You turn the beam on and you treat with her holding her breath. What is the advantage of holding her breath? If we are treating her left side, if she takes a deep breath, she fills her lungs with air and the heart moves away from the treatment beam. It's called breath hold. So we say, take a deep breath, hold it. She holds her breath. We watch it. We watch it on here to make sure it's within the green lines. We turn the beam on. Because it's a modern accelerator and delivers a very, very high dose rate, she only has to hold her breath for 20 seconds. 20 seconds, and the treatment's over. And by doing that, you treat the breast without treating the heart. It's called a breath hold technique that you can do with the linear accelerator and image motion management. Another thing that a modern accelerator has, I called onboard imaging. Here is the linear accelerator head with the bending magnet directing the beam toward the patient. You see the immobilization here for his legs. This head right here is an X-ray tube. This is a CAT scan. So the first thing we do is we scan the patient, and the radiation goes through the patient onto an imaging plate here, electronic imaging. We take a CAT scan of the patient before we turn on the beam. When we do that, we can compare the daily cone beam CT, the cone beam CAT scan. We compare that to what the patient was planned with on the first day of planning. And the therapists can line up the bones or can line up any marker and make sure that the patient is exactly in the same position as when he was planned. The therapists do that. The table adjusts. You can actually see the table move after the CAT scan. The table moves so that the target is exactly in the same place as when we planned it. So if you combine that with motion management, you make sure that the tumor is in exactly the same place day to day. And then you use IMRT to shape the field and avoid complications to surrounding normal tissue. So, what is old and what is new? Well, I like to say it's all relative. So, orthovoltage is old, but we still use it for skin cancer. The Van de Graaff generator that I worked on early in my career was very old technology, but its energy was beginning to get close to cobalt. So then came cobalt. So cobalt isn't the best way to treat deep tumors, but it is still used in many countries because the machine hardly breaks down. And it may be all that that clinic has to use for the time being. So yes, it's old therapy, but it may be all that the clinic has. And the advantage is these machines hardly ever break down. We still use Cerabend, even though it's old, we still use it for shaping electron beams. And that's actually, Cerabend is actually being used in proton therapy beam shaping. Solid wedges can be put into a beam to shape it, but they work well, no moving parts. Radiographic film has been replaced with portal imaging, but at least it's something if that's all the clinic has to verify beam placement in a port film. 2D planning may be all the clinic has. The progression would be from 2D to 3D to IMRT conformal. Some clinics don't have CT scanners. A lot of clinics, I would imagine, don't have CT scanners, but a radiographic simulator still works to give simulation films of the area to be treated. And many places are still using paper charts. It is still a record of the treatment. So the goal is to introduce new technology. Dual energy machines, 6 MV and 10 MV. So a machine that actually produces a 6 MV beam and a 10 MV beam. A dual energy accelerator with electron capability. Multi-leaf collimators. Enhanced dynamic wedge, where the jaw is moved during treatment to shape the field instead of using a mechanical wedge, and it does give a sharper beam edge. Intensity modulated therapy, IMRT, and also volumetric modulated arc therapy. Sweep the machine 360 degrees, move the linear accelerator with the beam on, shaping the fields the same time that the Linax is rotating. Higher output dose rates, up to 20 gray per minute on some of these machines. Onboard imaging for targeting. Image guided radiation therapy, where the daily CT image is compared to the planning CT, and the patient is adjusted. Breath hold for breast cancer to get the heart out of the way. Better immobilization. Multi-slice CT scanners that give you 3D treatment planning. And then a network to tie it all together so that the CT scanner talks to the treatment planning computer, which then talks to the linear accelerator, and everything is recorded in an electronic chart. So conclusions. Higher energy, lower dose to the skin, better skin sparing. Cobalt units have certain advantages, especially mechanical, but they're being replaced by linear accelerators today. Accelerators haven't really changed the way they make radiation. They still they all accelerate electrons near the speed of light. hits a tungsten target, out comes X-ray. But what's happened is the control of that beam, the control, the shaping of that beam, the monitoring of that beam, higher dose rates, much shorter treatment times, less chance of patient motion. Optical surface monitoring, I showed you with the cameras in the room that look at the patient's surface and make sure that it doesn't change during treatment. Breath hold to get the heart out of the way when you're treating the left breast of a patient. Onboard imaging for imaging, targeting, and treating. The use of multi-leaf collimators and higher dose rates to improve dose targeting. This is the end of the lecture. I thank you very much. I'm available for questions, but I will also, since you have this lecture, please look at some further reading here. You all have this, so you can look at further reading. And also, there are many slides here that I'm not going to talk about, but they're included in your lecture, and you can actually follow the progression. And it goes into a little bit more detail of things that we talked about today. So please take the time to review. Please take the time to review the slides that are included in this lecture that we don't have time to speak about. And I thank you very much for your attention.
Thank you very much, Frank, for presenting. I see some people have their hands raised, so I'm going to unmute you so that you can ask your question.
Okay.
So, Sundev, you have a question? Yep. Feel free to ask. All right, he might not have his hand raised on purpose, so about Chibi? All right, well, in that case, if anyone else has a question, they can raise their hand. There's also a few questions in the Q&A that I'm going to read out loud. If Frank, you're okay to answer them?
Absolutely. Yes, I'm here.
All right. So from Malamadad, after photon interaction, SEC electrons are responsible for the energy distribution. Then how about electron energy treatments?
So I didn't talk at all about electron energy treatments, but in a modern linear accelerator, they all have the ability to remove the target. I'm going to go back here. I think you can all see this. I'm going to go way back here. Let's do this. Might make it easier. If I go to, let's see, where do I want to go? Hold on. I'm going to answer your question in a moment. Okay, right here. Yeah. So let's look at this. Look at this picture here. See this target? This is the target here. So the electrons go around the bending magnet and hit the target and produce X-ray. But the question is, what if you take the target out of the beam? Well, you remove the target from the beam, and now you can treat the patient with electrons. You remove the target, you remove the flattening filter, and you put in instead a scattering foil to scatter the electron beam. And the patient can be treated with an electron beam that has been spread out. The advantage of electrons, or one of the ways electrons is used, is that electrons do not penetrate very deeply. The electrons can be produced by the linear accelerator, and they can be made to penetrate up to a depth of about 2 centimeters or 3 centimeters or 4 centimeters, and then they stop. They stop very quickly. So I didn't speak about electron treatments, but certainly electron treatments are important with linear accelerators in treating skin cancers, in treating lymph nodes that are very close to the skin, or if the surgeon has made a scar on a breast cancer and taken the tumor out, and the doctor is afraid that there may be some cancer cells in the scar, you can treat the scar of the tumor. You can treat the scar of the surgery with electrons to kill any cancer cells that are in the scar. So electrons have a very different depth dose than photons. X-ray photons fall off very slowly. But if we look at an electron depth dose curve, and I don't have one here to show you, but I'll show you what it looks like graphically here. Yeah, this is a good. See this picture here? An electron depth dose curve would almost look like a superficial curve. It would start up and then fall off very, very quickly. And most electrons disappear by a depth of about 6 centimeters. So the electrons mimic a superficial treatment, but they give a much more uniform dose. And instead of it curving this way, an electron would curve straight down, almost like a slope straight down. So yes, electrons can be used clinically for tumors that are very close to the skin surface. That was a good observation.
All right. Thank you, Frank. And then the next question is, was skin sparing concept there before Cobalt 60?
No, there was no skin sparing before Cobalt 60. Maybe with the Van de Graaff generator. Here's a picture of a Van de Graaff generator. Let's see. Do I have I know I have a Van de Graaff generator in here somewhere. Okay, let's do this. Hold on. I'm going to show you a Van de Graaff generator. This is a Van de Graaff generator. Look at the size of this thing. Oh my God, look at that. Van de Graaff generator. Now, Van de Graaff generators operated at about 1 MeV. There was a little bit of skin sparing with the Van de Graaff generator. Not much, but a little bit of skin sparing. It wasn't until Cobalt at 1.25 MeV that we started to see skin sparing. And that skin sparing is only 5 millimeters, but it did make a big difference in helping to prevent skin burns. If you can give the dose below the surface of the skin will not burn. But orthovoltage, superficial, always gave maximum dose to the skin. It wasn't until Cobalt that we really started to see skin sparing. A half a centimeter doesn't sound like much, but it helped a lot with keeping skin burns to a minimum. The early treatments were limited because they gave maximum dose to the skin, and also because they were not in the megavoltage region. They were always like 200 kV or less. Bone dose was very high. Bone dose was 2 to 3 times the dose to the tumor next to it. So the doctors not only had to worry about skin burns, but they also had to worry about bone necrosis because the dose to the bone would be so high. So early treatments were very, very limited. Cobalt changed all of that. Cobalt gave some skin sparing, and Cobalt, because of the energy, if you look at stopping power ratios, I don't want to get too into the physics here, but if you start looking at stopping power ratio for the different tissue types, you see that as you approach higher and higher energies, instead of the photoelectric effect, you have the Compton effect. The Compton effect ends up treating all of the tissues as about the same density, not a big change in tissue density with using higher energies, more so with lower energies. So early therapy, not only skin burns and bone necrosis, but you were limited. You were limited in how much dose you could give because of the side effects. But now with modern therapy, you can focus the beam so much that you can avoid the surrounding tissues and get the beam very, very exact where you want it. Give higher doses, less dose to surrounding tissue, less side effects. So yes, Cobalt was really the beginning of where the doctors were taking advantage of skin sparing. Next question.
All right. Thank you again, Frank. This one comes from Kwame. If a Cobalt 60 source reaches its half-life, is it advisable to use it for a period of time before changing the source?
Okay, very good question again. All good questions. The half-life of Cobalt is about 5.3 years. And at least in the US, we would change the source after one half-life. So pretty much every 5 years, the source would get changed. Now, the problem, of course, with using a source beyond its half-life is that the treatment times get longer and longer and longer. Now, the output from a Cobalt unit is usually less than 100 centigrade per minute. With the linear accelerator, you have easily over 400 centigrade per minute, 500 centigrade, even 600 centigrade per minute, very common in a linear accelerator. Cobalt, with a fresh source, could be 100 centigrade per minute, even 80 centigrade per minute, depending upon the strength of the source. Usually these are 10,000 Curie sources that go in. Now, the problem with using it beyond its half-life is the treatment times get much, much, much longer. If a patient has to lie on a table for 10 minutes for treatment, first of all, the patient is going to move. In 10 minutes, the patient has to fidget and move. The table's not that comfortable. The patient starts moving, coughing, breathing. Things change, all while the beam is on. The body position is moving. You're missing the target. You may be irradiating normal, healthy tissue. Second, in a busy clinic, you can't treat as many patients because it takes longer to treat the patient. So I like to say, dose is dose. So whether you give, you could give 70 gray with the linear accelerator, you could give 70 gray with the Cobalt machine. It's going to be the same dose. It's going to do the same damage. It's going to do the same harm. But how you deliver that dose is so important. Ideally, you deliver it in a very, very short treatment time. So there's less motion. And you deliver it under control with multi-leaf collimators. So how you deliver that dose becomes very important. But if your dose rates become very low, then the treatment times become too long. I'm not concerned so much about the biology of what's going on, because at those dose rates, the biology is pretty much the same. But the big concern is going to be patient motion. And then a secondary concern would be how many patients you can treat in a day.
Still have a few more questions
Good.
here.
Yeah, great. Keep them coming. These are good questions.
All right. So Zaka asks, the breath holding technique is beneficial for all left breast patients?
Okay, well, we generally use it for left breast patients. The problem is that sometimes women can't hold their breath too long. We prefer to use it, and if we can use it, we do, because you can see the advantage right here. We've become very concerned about dose to the heart. Very concerned about dose to the heart, especially portion of the heart that contains a very important artery called, I believe, the LAD, the left anterior descending artery, which is located up in this area here. And there have been papers presented at meetings and in journals that show that women who live a long time after breast treatment, women can live. Breast cancer treatment is very effective, as effective as surgery for early stages. So women live a long time after breast treatment, but then they develop heart disease. So the goal that we've been trying to do is to get the heart out of the way. And the best way to do that is by breath hold. So if a woman can hold her breath, and we see the advantage when we CT scan the patient. We do it both ways. We actually take two CTs. We take a CT with a breath hold, and then we take another CT with normal breathing. And if it makes a difference, which it usually does in most cases, then we prefer to use the breath hold technique. But it may not be for everyone, because some women just can't hold their breath for 20 seconds. And if they can't hold their breath, then they're not going to be a good candidate for it. And there's nothing else you can do but treat with normal breathing. But we treat with normal breathing for the electron boosts. So that's why another reason we do two CT scans. We do a CT scan with breath hold and evaluate it. And then we do a CT scan, normal breathing, because if we're doing an electron boost, let's say in this area here, we're not worried about the heart anymore. So with the electron boost, we say you don't have to hold your breath. So for the electron boost, you use normal breath hold, normal breathing, and you treat the scar with the electron boost. So we always do two CT scans. Hold your breath, and then normal breathing. We compare the two. If she can do it, we proceed with breath hold. If she can't, We use normal breathing, and we always use normal breathing for the electron boost because the heart is not an issue with the electron boost because the electrons don't penetrate that far. Okay, another question, please.
I think Ty just put something in the chat.
In the chat. Okay. Ty just said the advantage of cobalt is only mechanical and it's durable. Does not have any dose coverage advantage like head and neck CA.
Yeah, I don't see an advantage with cobalt for head and neck with linear accelerator. In fact, a lot of the papers that came out with at the beginning of intensity modulated radiotherapy, IMRT, intensity modulated radiotherapy, were focused on head and neck cancer because the papers were showing that the side effects became minimal with intensity modulated radiotherapy because, say, for example, you could have better sparing of a parotid gland on one side. You could have better sparing of the optic nerve. You could have better sparing of the optic chiasm. You could have better sparing of normal healthy brain if you're treating head and neck or even not, I shouldn't say brain because that's out of the way, but if you're treating head and neck cancer, better sparing of, say, the esophagus. So yes, with cobalt you could still get the dose in. It had to be shaped with cerebin blocks. I remember many times having to pour these cerebin blocks that protected the spinal cord with lateral opposed fields. But the dose coverage with linear accelerators, intensity modulated radiotherapy, shaped field, much better than with cobalt. You're dose limited with cobalt because of dose to the normal surrounding healthy tissue, especially the eyes, especially the spinal cord, especially, say, the parotid glands, if you're treating in that area. Dose limit is always a consideration. If you can deliver the same amount of dose or even higher dose while sparing normal surrounding tissue, you're going to get better tumor control and you're going to get less side effects. But most of the early studies that were done with IMRT were actually focused on head and neck patients that did much better with IMRT than with conventional 3D therapy. Okay, more questions, please.
Yes, we still got a few more. This next one is actually just a comment from Michael Osei. He says, I've happened to work with both Cobalt 60 and Linax machines. I must say this lecture has been really inspiring.
Thank you. Thank you so much.
All right, our next question is from Longino. He says, what is the diameter of your CT bore?
The diameter of a large bore CT is 85 centimeters. I know there's even there's even a manufacturer that makes a 90 centimeter bore, but I consider anything above 85 centimeters to be a large bore, and ours is 85 centimeters.
All right, great. I see Ben is answering the next question, so I'll move on to Nicholas's question. How can one cater for the portal imaging dose in the cumulative treated dose on the Linax?
Okay, so good question about including portal imaging dose. So in the days when we did not have electronic imaging, when we had film imaging and the cassette had X-ray film in it with a lead screen, so the high energy radiation would hit the lead screen would release electrons, the electrons would darken the film. We had to give much more dose to make those images, and if you had to repeat it, there was even more dose. So there was always a debate in the days of non-electronic imaging. There was always this debate of should we include the dose or not. And I've seen it done both ways. I've seen clinics that always included an extra 2 gray per treatment or even 3 gray per treatment to account for the portal imaging. But keep in mind, the portal imaging now that's a large field. So usually it's a dual image technique where you take the shape field image, but then you also open up the collimator and take a bigger image so you can see the anatomy better. So it was actually a double dose. So some places would account for it and other places did not. And I think it really depended on the doctor, whether the doctor felt that That could be a dose limiting, because if you take a portal once a week for 4 weeks or 5 weeks, there could be an extra, say, 20 gray, 30 gray, 20 gray added if you were using film and lead screens. So is that significant? Well, maybe not as far as the tumor goes, but it might be significant if you're very, very close to a structure limiting dose like the spinal cord or a kidney. It could become more important. So it really was up to the doctor and the physicist to decide whether to include that dose or not. Now, here we are in the age with accelerators of electronic portal imaging. We do not add that dose because the dose is so low, because the imaging is so good with a lot less dose that we don't add that dose to our treatment. It's less than a centigray per treatment, so we do not add it. So, and most places that I know of do not add it also. There may be places that want to include it, but how you include it is going to be really difficult because of the treatment planning aspects of it. Don't forget, it's a large field. When you do a portal image, it's an image on an image technique, and there's always a large field. How do you model that large field on a computer planning system? You'd have to actually model a beam with a large field and include that in the treatment planning. So it's very, very difficult to say for sure what the dose is with portal imaging. But if the portal imaging is modern, it's good, it's sensitive, my opinion, don't worry about the dose. It's minimal. Okay, next question.
Gamma rays and photons, do they affect the same tissues?
Yes, and the answer is yes. Gamma rays and photons have the same effect on tissue. And I say that because of a radiobiology principle called the relative biological effect, the RBE, or you may even know it as the quality factor, the QF, the quality factor. So in the range that we use for gamma rays for cobalt and X-rays from a linear accelerator, even though the energy of cobalt is 1.25 MeV and the energy of a linear accelerator is 6 MeV, the radiobiological effect is the same. Photons and gamma rays have the same effect. Now, to analyze this even more, you have to look at target theory in radiation biology. This is a study in radiation biology and how radiation actually causes biological damage. As it turns out, gamma rays that we use from cobalt, from cesium, gamma rays from radium, gamma rays from iridium, all of the gamma rays that we use have the exact same radiobiology effect as the X-rays that we use from a linear accelerator, irregardless of their energy. And it has to do with target theory, where the energy that's delivered is very lightly ionizing, lightly or sparsely is the right word, sparsely or lightly ionizing. So as the energy enters the cell contains a nucleus. The nucleus contains the DNA. We're targeting the DNA. With photons and gamma rays, the DNA is destroyed, but only in single breaks, only a spot here, a spot there, one here, one there. And we know from biology that DNA can repair itself. We give it an RBE of 1. However, if you're talking about heavy particle theory like protons, heavy particle theory like pi mesons, heavy particle theory that cause a double-stranded DNA break, the RBE is much higher and the effect is much more damaging. So while dose is dose, you can give a centigray of gamma, you can give a centigray of X-ray. You get the same effect biologically. But if you gave a centigray of gamma versus a centigray of protons, the energy deposited may be the same, but the biological damage is different because they have protons, heavy particles, have a different RBE. E. So it all comes down to the radiation biology. Very good question that touches on radiation biology. I would encourage you to study the radiation biology behind the energy of the beam treating the tissue. Fascinating field of radiation biology and target theory within the cell. How many targets have to be knocked out before the cell can't divide anymore? There's a whole radiation biology. What I love to talk about, like the physics of radiation therapy and how as a physicist at night, if I'm calibrating the machine, I test my beam in a tank of water. I assume the patient is a tank of water, right? But the patient's not a tank of water. The patient has biology, and you have to look at how the radiation is affecting the DNA. So even though I'm a physicist and I'm looking at dose and I'm measuring the machine is accurate. I can tell the doctor, yes, this patient's getting 70 gray. There's a whole biology behind that takes place. And that's the other half of radiation therapy. So there's the physics of it, and then there's the biology of it. And I would encourage you to study the biology of the radiation also. Next question, please. All good questions.
All right. Michael asks, which cancer cases are best treated with Cobalt 60?
Well, for Cobalt 60, I think right now the thinking is palliative cases, bone mets, lung mets, brain metastases, any type of metastatic disease best treated with Cobalt where the dose is not that high. So you don't need to worry too much about normal surrounding healthy tissue. So my first thought is metastatic disease best treated with Cobalt. But what if that's all you have in your clinic? What if a Cobalt is the only machine that you have in your clinic? And then you're saying, what do I treat with it? Well, you can pretty much treat everything with it. There's no limit because, as I said before, dose is dose. You can give the same dose with Cobalt. You can give 70 gray to a tumor with Cobalt. You can give 70 gray to a tumor with a linear accelerator and IMRT. But look at the dose to the surrounding normal healthy tissue. That's where your limitation is going to be. So for breast, I think you can give the same dose, but there will be skin burning. There'll be more skin damage that you will have to treat in the clinic with different creams, with different medications. There'll be more skin burning. For head and neck cancer, you're going to be limited by dose to the spinal cord. You're going to be limited by dose to the optic nerves. You're going to be limited by dose to the parotid glands. So it's hard to say what's best treated with Cobalt. Dose is dose, and it really comes down to how conformal can you make it. So I know I didn't give you a very good answer for that, but there's a short answer, and it's metastatic disease best treated with Cobalt. But then people are going to say, well, that's all I have. What do I treat? And the answer is, well, you can treat anything with Cobalt. You've got to be really careful with the normal surrounding healthy tissue.
In 3D conformational RT, in 3D conformal RT, some Linax have multiple leaf collimators, but the tumor is not well shaped. Can you give reasons for this?
Yeah, well, tumors come in all different shapes, and they have all different clinical spreads to them too. So it's hard to really define an exact tumor shape that's the same. They're not the same. They're very different. So this is where careful treatment planning comes in. Now, yes, you have multi-leaf collimators, so you can shape the field better. But how far beyond the tumor do you shape the field? And this is where the very, very, very important concepts that you have to study of GTV, gross tumor volume, CTV, clinical treatment, clinical tumor volume, PTV, the planning treatment volume, and then the ITV, the image treatment volume, or the image tumor volume, the image treatment volume, you can call it. So these are very important concepts that become critical in modern treatment planning. So the doctor is responsible for defining the tumor, and the doctor has to know how far beyond the visible tumor cells have spread. And then the physicist has to help the doctor understand the penumbra of the beam and how close to the edges you can get, and that determines the planning treatment volume, the PTV. Now, the PTV is what's going to be treated, and hopefully it's as conformal as possible. I'll give you some examples from our clinic. Prostate cancer. We treat a lot of prostate cancer. Now, in prostate cancer, we define our PTV as 8 millimeters away from the anterior of the prostate and 8 millimeters away from each side of the prostate, left and right. However, in the case of the rectum, which is so close to the prostate, we cut that way, way down to 5 millimeters or less. Now, prostate cancer, depending upon its stage, could be well confined to the prostate. So it's an easy cancer to treat because the cancer is confined to the capsule of the prostate. And you can very accurately put these PTVs around it. And that's what we treat. And we spare the rectum. We spare the femoral heads. We spare the bladder. We can shape the radiation to just the prostate and spare everything else around it. Okay? Now, one of the things that we do in our department, and I did not talk about this, but it's called image fusion. And this gets back to the question of how do you define a tumor? So when you have a department that has a networked computer system, treatment planning, connected to the CT simulator, connected to the radiation treatment machine, the patient, many times the patient will not only have the CT planning film or image set, but the patient can be sent to a different hospital for an MRI or for a positron emission tomography, a PET scan. So the patient goes to, say, Rhode Island Hospital and gets a magnetic resonance imaging of the brain, of the head, right? Now we're treating a tonsil tumor, or we're treating a base of tongue tumor, or we're treating a nasopharynx, for example. Now, one of the things that we like to do, and we do this routinely, is that, as a lot of you know, the CT scan is very, very good. The CT scan is very good in terms of resolution, but the MRI gives better soft tissue resolution. So we do a process called image fusion, where we take the image from the MRI and we put it on top of the CT image, and we can change the color of it a little bit, and we fuse them together. So now some soft tissue, let's say soft tissue invasion or soft tissue effects that you could see on the MRI, you can't plan from the MRI, you have to plan from the CT. But if you fuse the MRI to the CT, you have the advantage of seeing both, and the doctor can switch back and forth very quickly, back and forth between the two, and see where the tumor extends to. And if you can even put a positron emission tomography scan on top of that, which is very sensitive for cancer. And it may show that cancer is beyond what the doctor sees on the CT scan. So by fusing the two images together, you can better define what you want to treat. So there are different modalities of imaging that you can combine when you have the computer capability to do that. So it's very hard to define a tumor on a plain X-ray. Very, very hard to define a plain tumor on an X-ray. You may be able to see differences of 20% or more on a plain X-ray. It takes 20% or more to see a difference on an X-ray. On a CAT scan, it takes a difference of maybe 2 or 3% to see the difference. But on an MRI, you could see differences of less than 1%. So if you could combine hold on, I got to take a drink. If you can combine the advantages of each modality in a fusion, the doctor has so much more information to work with, and you can get a better idea of where you want to put that PTV. And I want to finish this question with one more thing, the ITV. So if you're taking a CAT scan of the patient, you can actually put a monitor on the patient that checks for breathing. And every time the breathing is in a different position, you take a different CAT scan. So you now have a movie, a CAT scan cine movie of breathing. You can actually make a movie, not just static images, but with these CAT scans and with 4D, they call it 4D imaging, where you're looking at movement. You can create a movie of the movement. So let's say you have a lung tumor and it's clearly defined on CAT scan, but when the patient inhales, the lung tumor moves up, and when the patient exhales, the lung tumor moves down. Now you have to treat the patient while the patient is breathing. So actually the target is moving during the beam on. The doctors create an image volume where they actually look at the extent of the tumor movement and draw around it, and that's what they want to treat. So the tumor is always in the field. Now you can take that even a step further in a process called gating, G-A-T-I-N-G, gating, where the accelerator can be programmed, the linear accelerator can be programmed to give its dose just during expiration. So when the patient breathes out, a burst of radiation, and then the beam stops while the patient breathes in. The patient breathes out, bam, another burst of radiation. So you can treat the tumor in exactly the same place every time by gating the beam of the linear accelerator. You cannot do that with Cobalt. That's another advancement in planning, where you can gate the beam to only be on when the tumor is at a certain location, like expiration of breath. So yeah, good question about how to define the tumor, the clinical extent of the tumor, and then the PTV, the planning treatment volume that you have to treat. And again, remember, maximum dose to the tumor, minimal dose to the normal surrounding healthy tissue.
If you want to talk, I also see that you have a question in the chat. If you want me to just read that. Yeah, I'll just go ahead and read it. So they ask, what is the difference between true beam Linac and variant beam Linac?
Okay, so Varian, as you know, is a linear accelerator manufacturer, which just last year was bought by Siemens. So Siemens now owns Varian. A true beam is one of the most modern Varian Linacs on the market today, the true beam linear accelerator. It's not the latest product that Varian came out with. Varian came out with even a more modern machine called the Halcyon. But let's talk about TrueBeam. So TrueBeam is today a very modern, state-of-the-art linear accelerator. The TrueBeam has certain advantages that other Varian Linacs did not have. One of the principal advantages of the TrueBeam is that it's capable of very, very high dose rates. So true beams typically operate at over 1,000 centigrade per minute. Now with a true beam machine, you can remove the flattening filter. So remember we saw, let me go back here. Remember we saw, let's look at here. Okay. Now, from the current slide. So, okay, here's the flattening filter, this cone right here. On a true beam machine, you can take that filter, you can take it out. You can take out that filter. Filter's made of tungsten. Take it out, gone. You don't have a flattening filter. You say, well, you need a flattening filter. How do you spread the beam out over 10 centimeters, 15 centimeters, 20 centimeters? You need a flattening filter. No, you don't need a flattening filter. You can treat with a very intense lobe, what I call almost like a bullet of radiation. Because if you're going to deliver intensity modulated radiotherapy, you deliver it with very small fields anyway from many different angles. Why do you need a flattening filter? Take the flattening filter out, treat with a bullet shape of radiation, and without the flattening filter, you double the dose rate. Without the flattening filter, you get 2 1,000 centigrade per minute. It's a crazy amount of energy in a short burst of radiation. So if you can model it on your treatment planning system, you can have your treatment times very, very, very short, like less than maybe, I don't know, 15 seconds, 10 seconds. I know the treatment times become ridiculously short for the beam on times because you've removed the flattening filter. So TrueBeam lets you do that. TrueBeam is a machine that can be used for any type of cancer. It can be used for standard radiation therapy. It can be used for breast, prostate. It can be used for GYN. It can be used for anything. It can also be used as a stereotactic radiosurgery machine because you can get it with very high definition leaves, multi-leaf collimators, so the fields can be shaped into very small circles or into very small ellipses. You can shape the field to very small fields and deliver very, very high doses of radiation in a short period of time. So the TrueBeam is set up for stereotactic radiosurgery, SABR, SABR, stereotactic ablative body radiotherapy. The TrueBeam is set up with imaging built into it. The TrueBeam comes with a table that moves in 6 different directions. Not only up, down, in, out, left, right, but it has all of the rotational axes built into it. So it's called 6 degrees of freedom table or a hexapod table. 6 degrees of freedom. And you use that for when you image the patient with the onboard CT scan on a TrueBeam, you target the tumor, you tell the machine you tell the table to put the patient in that position. The table moves the patient to that position. You turn on the beam, treatment lasts seconds, and you're done. And it's all conformal because it's all intensity modulated. So yeah, TrueBeam is the top of the line of the standard variant Linax. And then there were all the other Linax before the TrueBeam. There was the Trilogy system. There was the Clinax series before that. So the variant went through this whole evolution of machines, and it stops at TrueBeam, and then they're moving on to a CT gantry style, like tomotherapy machine. Variant is now making its most modern accelerator looks like a tomotherapy machine, and it comes with CT imaging included, plus tomotherapy beam delivery, and you're going to see also MRI included in these new machines. So they're going to go from a CT image guidance to MR guidance, which gives the therapist even more information to target the tumor by. Yeah, so hopefully that answered your question. So TrueBeam, top of the line, conventional accelerator. Interesting that Varian was bought by Siemens. That happened about a year ago. I was surprised because Siemens used to make their own linear accelerators. The other big player in the market, of course, is Electa. Electa comes out of England. They make a machine very comparable to the Varian TrueBeam. It's called the Electa Infinity with an agility collimator. 160 leaves on the Electa collimator, 80 leaves on each side, 160 leaves shaping the field, all different crazy shapes that you want. Okay, next question.
All right, I think we have 2 more. Also,
Sure.
just as an FYI for others, the answered section of the Q&A has answers to some of the questions that Ben and Elaine are nice enough to answer. So if you want further information on that, feel free to look in that section. All right, so this question comes from Vincent. Having worked on Cobalt, if you experience shifting of patients from Linax to Cobalt and vice versa, how did you manage the dose being experienced physicist if you had, and if not, what's your take?
Patient position and shifting patients from Cobalt to Linax. I think the question has to do with immobilization, patient movement in Cobalt, patient movement in a Linax. Because the treatment times with Cobalt tend to be longer, patients are going to tend to move. You can't help it. Patients, they always move on a table. You can't help it. They breathe, they get itchy, they want to shift their shoulders, they want to move their head a little bit. And you may not even see some of this motion on a TV, on a TV monitor that you're looking at the patient with. In fact, I've worked on cobalts so early in my career. This is crazy. What I'm about to tell you is you're not going to believe it, but I go back a long, long time. And I actually worked at a center where the Cobalt unit had a big, thick lead glass window on the entrance door, a mirror that would reflect to the patient, and you were looking at the patient through a lead glass window, looking at a mirror at the patient. You didn't even have a TV monitor in the early days. So imagine trying to see patient movement when you're looking directly at the patient without a monitor that you could, zoom in on the patient. I mean, but that's how it was. So with Cobalt, long treatment times always mean patient motion. Patient motion means you're not targeting, you're not hitting what you thought you were hitting in your planning system. Your planning system assumes the patient is perfectly still, like a tank of water. Patients are not a tank of water. They're going to move. And if there's movement, then your targeting is going to be off. So the change that I noticed was shorter treatment times, better immobilization too. We've improved a lot with our immobilization techniques. We've improved so much with our immobilization techniques that patients, pretty much are locked down pretty tightly now, especially with the masks that we use for head and neck cancer. The masks extend all the way down to the shoulders and lock everything down to the table. So patient motion, patient movement from Cobalt to a Linax, unless you have really, really good immobilization, the long treatment times mean that your immobilization has to be better. In a Linax, if you're delivering dose in a matter of seconds, there's not going to be a lot of movement. In a Cobalt unit, if you're delivering treatments in the order of minutes, and it could be 5 minutes, could be 8 minutes, could be 10 minutes, there's going to be much more patient movement. So your immobilization has to be even better. I hope that answered that question.
All right, great. And our final question, Timom asks, why we use cobalt beam quality over Linax during calibrations of the dosimeters?
Because that's a very, very good physics dosimetric question. Cobalt is nature. Cobalt 60 is nature. It is made in a nuclear reactor. By the bombardment of stable cobalt 59, it becomes cobalt 60, highly radioactive. The energy of the isotope is precise. It doesn't change. The energy is exactly, cobalt emits 2 photons. Okay, one at 1.17, the other at 1.33. The average is about 1.25. It never changes. It doesn't care what the barometric pressure is. It doesn't care what the weather is. It doesn't care about the electricity coming into the building. It doesn't care if there's a power failure. It doesn't care if the electricity is high that day, the electricity is low that day. Cobalt is the same. It's nature. It never changes. It makes a perfect standard. And it has the same quality as a photon beam, as a linear accelerator X-ray beam, but its advantage is it's the same everywhere. It never changes. Cobalt is cobalt is cobalt. The energy is precise. So the scientists that came up with the different calibration protocols knew that they had to have a standard. They came up with two. They came up with two things that you can never change. Cobalt, the energy of the cobalt, always the same, never changes. And water. Water is the same everywhere. Fresh water taken from the tap, the same everywhere. So the calibration protocols that I follow, the chamber is always referenced to cobalt, and then factors are applied to that. There are different factors that are applied to your cobalt factor to correct it for the linear accelerator energy that you're using. But as far as the standard instrument, the Farmer chamber, the dosimeter that you use to measure the beam, it's referenced to cobalt and it's referenced to water. So it's not referenced to plastic. It's not referenced to polystyrene. It's not referenced to any of the plastics that are out there. It's not even referenced to solid water. It is referenced to liquid, fresh water. Cobalt doesn't change. Water is the same. Those are your two standards. Once you have that locked into your chamber calibration, you can then add factors for the energy like 6 MV, 10 MV, 15 MV. You can apply different factors to correct that calibration factor, but your calibration factor is solidly and perfectly based on two things that never change. And that's why you use Cobalt.